Hello everyone, Miranda Pickett here, and this is my Advanced Concepts presentation for Module 3. I'm at work again, as you can see, as usual, on a 48-hour shift, and we're also preparing for this hurricane coming, so I'm going to make this as quick as I can, and hopefully you enjoy. So a little bit about what we're going to be discussing today. I'm going to start off with some background information, just about heme and hemoglobin, and then I'm going to talk about some hemoglobin structure because I think it's good to know the structure so that you can understand the binding properties. Then we can put it all together and talk about how oxygen actually binds to the hemoglobin, uh, and we'll be talking about the binding capacity between the lungs and the tissue capillaries. And then lastly, we'll talk about CO2's interaction with water and what happens with or without water. So first things first, we'll talk about background information, and I threw a couple of interesting facts in here because I thought they would kind of really get your mind going. So the first fact is that the average adult consumes oxygen at the rate of 250 milliliters or the equivalent of 250 milliliters of oxygen, pure oxygen per minute. However, only about 1.5% of that is actually transported in the plasma in the blood. The majority of the rest of the oxygen is actually carried by hemoglobin, and hemoglobin is composed of 4 groups of heme. The most common metal in the body is iron. Well, commonly used metal in the body is iron, and in fact there are 4 iron molecules in each hemoglobin protein. There'll be 1 iron molecule in each heme, and there's 4 heme groups in each hemoglobin. And then another important thing to remember is that the binding of oxygen in the relaxed state is an allosteric process, and we'll talk more about that later. So the general structure of hemoglobin, I'm going to move my camera so we can see a little bit better, and hopefully I'll remember to move it back. Okay, so the general structure is that it's a quaternary structure and it has 4 subunits, 2 alpha units and 2 beta units, and they're often referred to as alpha-beta dimers. It'll be set up as alpha 1, beta 1, plus alpha 2, beta 2, which all come together to form a tetramer. As I said earlier, there's 4 hemigroups, subgroups, in the entirety of the hemoglobin protein. And each hemigroup also has, as you can see here, an iron molecule kind of, I'll say in the middle. But we have beta chain 1, beta chain 2, alpha chain 1, and alpha chain 2. And these are 4 polypeptides that come together to make an entire hemoglobin protein. And then here you can see these little disc, little pictures are the heme, and then the little dot in the middle is your iron. So moving on to a more specific structure of hemoglobin, as I said earlier, I kind of pulled these over to the slide so that we could see a little bit better. So we have 4 subunits, 2 alpha, 2 beta, or they're known as alpha-beta dimers, forming together to form a tetramer. And as I said earlier, there's 4 hemigroups that come together to make a hemoglobin protein globulin. So there's 2 specific structures that we're going to see the hemoglobin in. The first one is deoxyhemoglobin, and this is where the oxygen is not bound to all of the hemes. This is known as the 10th state, the T state. In this state, the hemoglobin has less affinity for oxygen, and it's also in a non-planar configuration. And I put this image down here because I think it shows a really good view of deoxygenated versus oxygenated hemoglobin. So over here you see the deoxygenated, and you see they're like not in a straight line and not on the same plane. So non-planar, T-state, deoxyhemoglobin. The other one is oxyhemoglobin, and I think it's pretty self-explanatory that oxygen is bound. This is the relaxed state, the R state. In this state, the hemoglobin has a higher affinity for oxygen, and it's in the planar configuration. And if you look over here with the oxygenated portion of this image, you can see I kind of view it as a straight line with our iron in the middle. Again, planar, higher affinity for oxygen, relaxed state, oxyhemoglobin. Now we can move on to the binding of oxygen to hemoglobin. And in order for oxygen to bind to hemoglobin, the hemoglobin has to transition from the T or tense state to the rested state. So the first thing that's going to happen, and I brought my images over here too so we can kind of visualize. The first thing that's going to happen is that the iron is going to move onto the same plane as the porphyrin ring, which will cause, let me go back, which will cause the planar configuration with this image over here. The histidine residue that's bound in the 6 coordination that's also associated with alpha helix will also move to the plane of the porphyrin ring. So we are kind of bringing everything up to the same level here. The 2 alpha beta dimers will rotate 15 degrees around each other, and that will stabilize the protein, which effectively transitions it from the tense state to the relaxed state. At this point, the oxyhemoglobin formation is there, and it's got a high affinity for oxygen. It'll start off with one hemigroup accepting an oxygen, and then once that happens, the 3 other hemigroups automatically transition from the T state to the R state, and they collect oxygen molecules too. And this is what I was talking about earlier with the allosteric property of being oxygenated. Gaining oxygen to carry to the other tissues. Moving on, let me see if I can I'll put it as well as I can on my camera. Now we're going to talk about the binding capacity of oxygen in the lungs and the tissue. I thought this image up here was a really cool image because it kind of shows that when they have a low affinity, the hemis are kind of closed off, so they're not going to accept the oxygen. And over here we have the high, where they're kind of open up wider and they will accept the oxygen. So our binding capacity of oxygen is affected both by the pH and the torr, which is your partial pressure of oxygen. Oxygen from the lungs going to the hemoglobin causes a sigmoidal curve here on our graph. And and you can see it here, it's an S. What this signifies is that it's cooperative binding. If the O2 is going from hemoglobin to the myoglobin, which is in all your tissues, you're going to have a hyperbolic curve, which means non-cooperative, and it's going to go up and over. In the lungs, the pH is about 7.4, which is high, and has a torr of 100, which is a high oxygen partial pressure. The increased torr and high pH do not allow for salt bridges to form over here between the aspartate and the histidine, so they have an open hemi, here, so they can accept the oxygen. In the tissue capillaries, the high CO2 levels in the tissues will actually lower the pH and the torr. In the tissue, you're going to have a pH of about 7.2, which is lower than 7.4, and a torr of 20, which is a low oxygen partial pressure, so the oxygen is naturally going to want to go over into the tissues. The binding of CO2 causes the R state to go to the T state, and the side chain of the histidine beta 146 becomes protonated, which allows for the salt bridge formation with aspartate, causing the release of CO2, which oxygen, which stabilizes the T state. Also, something else that helps with the oxygen coming off the hemoglobin is that the hemoglobin will react with the CO2, and it decreases the O2 affinity as well. So the takeaway from this is that high binding capacity in the lungs and a low binding capacity in the tissue capillaries. Last but not least, we'll talk about carbon dioxide and water interaction. So basically this is occurring to begin with in the inside of the cell. The CO2 reacts with the water and forms carbonic acid. The carbonic acid dissociates to form bicarbonate and hydrogen, positive hydrogen. So it also removes the hydroxide ions, and this results in a decrease in the pH. The drop in the pH causes a release of oxygen into the capillaries, allowing them to be oxygenated. So we have no problem, our tissues are being oxygenated oxygenated, we're good to go. Without water, if the carbon dioxide doesn't react with water, we won't get a carbonic acid to be formed. We won't get our dissociations. We won't get the bicarbonate and hydrogen, which would mean that the pH is going to increase instead of decrease. So this would not allow for the oxygen to be dropped off in the tissues, and obviously without oxygen in the tissues, we're going to start becoming hypoxic. And long enough without oxygen eventually will lead to cell death and tissue death. Oh, and this is a cool little graphic here that kind of shows the CO2, your bicarbonate, your positive hydrogen. All right. So in conclusion, we talked about the background information that I thought was important with the oxygen and the iron. We also talked about hemoglobin structure, both general and specific. Then we talked about the binding of oxygen to hemes and hemoglobin. We also talked about the binding capacity of oxygen in the lungs and in the tissues, capillaries. And then we lastly talked about the interaction between carbon dioxide and water and why that's important. Thank you for listening and watching. I hope everyone has a great night. And all my references are right here on the next slide. Again, have a great night.